All right, and everybody got their official message that we're being recorded. And so again, our first speaker is Ricardo Campos. And if you want to go ahead and get your slides up, Ricardo will be talking to us about probabilistic wave forecast based on the NCEP's global ensemble forecast system.
All right, good morning or good afternoon. Can you see my slide?
Yes, and it's in full screen, so take it away.
Good, thank you, Jessica. Well, thank you all for inviting me for this presentation today. I'm very happy to be among this group. Today we'll be talking about probabilistic wave forecast. This is associated with a project involving the OPC, EMC, AOML. I'm a CIMAS assistant science at AOML. And, we have a clear motivation on what we need to be working on in this project. So we have accurate wave forecast for short-term period, the first days in lead time. But right now, NOAA doesn't have any current marine hazard forecast or information on the week 2 period. So this is something that we are currently working on and committed to develop a product that will be addressing this extended forecast range. So our main goal is to develop an oceanic hazard outlook, winds and waves, containing delineations of potential hazards for life and property at sea. And this is entirely based on the Global Ensemble Forecast System version 12. And before starting with the probability maps and the probabilistic algorithm, we need to run an extensive validation and then generate enough data to be working on that. So 1 or 2 years using archives is not enough. So we work hard on developing a reforecast data, preserving the characteristics and the grids of the system that's running operationally, but expanding to the last 20 years, actually from 2000 to 2019. So it's using the same grids and tuning as the currently operational GAPS V12. There are 2 polar grids and 1 global grid in the mosaic. And the output is in a 1/4 degree resolution. The operational system works with 4 cycles per day, and the reforecast, because of computational cost, it runs 1 cycle per day. And the operational system has 30 members plus the control member. And for the reforecast, we run 5 members, and once a week it extends to 11 members. Okay, so we generate the reforecast and we move on to the validation against buoy and altimeter data. So we selected 96 buoys in deep water. So it's a 1/4 degree resolution product. So it's not exactly the best for coastal waters. So we are focusing on deep waters far from the coast. And the initial validation, it's looking at different metrics, Q plots, scatter plots, and so on. And then we have here divided in day 1, week 1, week 2, up to week 5, right? We have an extensive forecast range that we can analyze. And so the QQ plots are showing very good accuracy for the control member and the ensemble mean. EM in red is the ensemble mean. So it means the model is it's very well calibrated. The optimization that has been run is excellent, and the bias is showing that it's confirming the same quality as it's pointed here in the QQ plot. And the week 1 is still holding a very, very good correlation coefficient and results. The QQ plot it's confirming that correlation coefficient above 0.8. And the degradation of the model occurs mostly around week 2, end of week 1. We will see that in more details, and then week 2 to week 5. scatter index of 15% here, and between 20 to 30% of scatter errors. And as we move to longer forecast leads, week 2, week 4, week 3, week 4, and so on, we see the ensemble mean that is it's completely changing, right? It's underestimating the highest C's and overestimating the small ones. So this tendency is very well known, and we could see moving to longer forecast range. This is how the scatter index is it's increasing with time, and it's nice to see the Taylor diagram, actually, the control member in blue and the ensemble mean in red. So far, I'm talking just on significant wave height. And then for the week 1, we are close to the this black line here of normalized standard deviation. And then as we move to week 2, 3, and 4, the ensemble mean preserves a better correlation coefficient, but then the standard deviation is reduced. So the variance is being reduced significantly, and this is why we underestimate the storms and overestimate the small waves. And this is an illustration of that, right? So far I showed some both metrics and results over 20 years. So this is an example of a storm in the Pacific Ocean. The top axis is showing the forecast lead time, 1 day up to 35 days. Red, we have the observations of HS, 9 meters in the peak of the storm for 1 cycle only. And then blue, the ensemble mean, and black, the control member. And we see the beginning, short forecast range, very well following the observations. And as we go to week 2 here, right, between 7 to 14 days, then the ensemble mean it is basically very constantly and almost flat, and the spread is very large as we expected. We see that in the wind forcing the waves, and also in the wave forecast. So we expanded the validation to altimeter data, which is excellent. We have global coverage, far much more data to consider, and we have a better view on the root mean square error and the other metrics as a function of the forecast time. So the first day with very small errors, and then between 3 to 4 to 10 days we have a high increase on the error, on the root mean square error. The ensemble mean is performing better than the control member or any individual members of the ensemble, as we expect, and it tends to be stable, flat after 12 or 15 days. And this here shows the telegram indicating that the short-term forecast is overconfident, and with the small spread. So we are working on it. Root mean square error, correlation coefficient. I draw attention to this part here. We have 0.96 of correlation coefficient in the day 1, which is higher than most of reanalysis data. So this reflects the very good product in the short range. And after 7-10 days, the correlation drops significantly. With the altimeter data, we can have a better spatial view of that, computing the metrics for each bin around each grid point. And this is the result for HS and wind speed, covering the 20 years of reforecast. And it's interesting to see the overestimation in red and underestimation in blue. Here we have overestimated simulations in HS on the eastern portion of the Pacific Ocean, close to California, Mexico, coast of Mexico, same as here in Central and South America. which is not seen in the wind field, the diameter wind. So it's indicating that probably the propagation of the swell it's allowing more energy and propagating more energy throughout the large basin, the Pacific Ocean. It's also interesting to see the effect of the wind speed with larger scatter errors on the warm currents located at the warm currents here, the Gulf Stream, Brazil, and also Kuroshio Stream, that's reflecting on the waves. So the significant wave height responding to the errors of the wind speed on the warm currents. And then we can see, moving from week 1, the benefit of the ensemble mean compared to the control member. Week 1, similar, but as we go to week 2, there's a large error on the control member that is preserved on the ensemble mean. So it reflects the benefit of the ensemble forecast compared to the deterministic forecast. But again, I go back to my example. The ensemble mean is not the best way to analyze a forecast after 7 days or after 10 days of forecast. It will be having this smoothing characteristic of the storms, making the peaks of the systems much lower, and also expanding the size of the storm, deteriorating the spatial view of the storm. So the ensemble mean, the control members are indicated here, but as we look at individual members, we can see the benefits of them plotting together. So none of them could capture the peak of the storm, but when we analyze all of them, we can see a situation here in week 2 pointing to a possible extreme scenario in this forecast range. So the situational forecast here is very rich. There's a lot of information that we can explore. Now it's a matter how to explore that, since we see that individual members and the ensemble members are not the best way to look at that. So the probability map algorithm that we are developing is intended to do that. It's been done for the atmospheric side for decades, for temperature, precipitation, CPC. It's doing that for a long time, and now we are adapting this for the wave forecast. So we selected period here, week 2 in this case, but it's flexible, right? You can select any forecast range, and then an optimal window that will account for the model, for the system actually to diverge in space and also in time. So this is representing this point here close to the buoy, in black and the ensemble members in red, for certain thresholds that we define based on the usefulness and the information that is going to the forecasters. And after including neighboring points in blue here, we can add all the information that we need to start looking at that probabilistically. And so if we consider all the members, we will have low probabilities of something above certain thresholds. But as we look more into the tail of the distribution, we tend to improve this analysis. So there are several parameters that need to be optimized here. The size of the window, the time, that's actually it's not fixed in week 2, the amount of data we select for each member. So we're taking the n maximum values, and actually n is equal to 2. So for each member, we select the 2 maximum over the week 2 period. And then we combine all that, subsample, and then extract just the tail of the distribution using a percentile, in this case, 87. So with that, we can calculate the probabilities of being above 15%, 50, 65, and 80% to facilitate the visualization and extract information from the maps. This that's showing here, it's for one single point. We are computing now for the whole globe, and using certain thresholds, 4, 6, 9, 14 meters of significant wave height. And then we are producing now as an experimental forecast this type of map here. So these are showing the probabilities here in the Pacific Ocean to be very high for waves above 9 meters, which is very extreme. And that is actually the situation that we checked to be valid for this period, for the week 2 period associated with this event that you probably remember as well, that hit the coast of California. And that is another view on the point, on the single point, on how we compute these probabilities. The area of the PDF is equal to 1, and the area on the right side of each threshold is what we compute as the probability to be above those 3 thresholds here that we are indicating. So here's the observation for this specific event equal to 5 meters. So it's a very good forecast in terms of information given by the probabilities on the right side of 4 meters. There were no false alarm, and nothing on the right side of 9 meters, and a small error with this area above 6 meters, indicating a small probability to be above 6 meters, whereas the observation was 5 meters. But it's not critical because this was a small error. These are examples of not very successful events. Overestimation on the left side, so the Ensemble members, the way we subsample the data and we build the PDF, it's showing much higher probability than expected. And the opposite, the observation here, the buoy measuring 12 meters, and most of the data, the forecast around 6 to 9 meters. And with that, we analyzed several systems and events, extratropical and tropical, dividing on true positive, false negative, and so on. That will be shown today. This is for the case in the Pacific Ocean associated with the Maersk loss of containers in the Pacific that was pointing again in Pacific Ocean probabilities of swell, HS above 9 meters. So the swell actually caused the accident in the Maersk ship. This is an unsuccessful case. So the Idalia, also Otis, was not very well captured by the system, so it's not pointing any information on the Gulf where the hurricane passed. This was a very interesting case and successful case for Hurricane Lee. Also, Hurricane Franklin was very well captured with probabilities of winds above 40 knots, and also waves. We checked waves above 6 meters and 9 meters. And this is the reference showing how it's matching and how the week 2 forecast could indicate with very high probability following the track of the system. This is very useful information. And then we start looking at more statistical analysis and more details, categorical and probabilistic view of that. I will pass it very rapidly. So the nice ways to use the ROC curves, true positive and false positive rate. So we want the curves to be close to this corner here, equal to 1, and this diagonal will be a not so useful forecast with lack of important information to extract. So this we can see for wind speed and 34 and 41 knots, the ROC curve and the area in the curve showing very useful information for week 2, 0.93 in this case. Also for the significant wave height, 4 meters and 6 meters with area under the curve equal to 0.91 and 0.85, which is also very useful. And the most challenging condition actually is occurring as we move to higher values of significant wave height, and also in the binary classification as we use 80% or more. So then the probability of detection will be decreasing, and the false alarm ratio will be very high. So the critical success index tends to be lower as we go to larger waves and higher probabilities. So we don't expect to see a 85% of probability of something around 6 or more, or 8, 9 or 14 meters in the week 2 range. We would tend to see something around 50, 65, 50 or 15% of probability. And that's our conclusion. So GAPS is showing very, very high accuracy, impressive results in the short term. We have challenges in the long term, as we always have. But by relaxing the requirement for exact matchups in time space, we can post-process and develop probabilistic models to provide useful forecast guidance. That's the key part of this study here. And results show that these probability maps are working better for extratropical locations and large meteorological systems. And the most challenging conditions actually occur for forecasts under hurricane, small, very strong winds and short patch, which is, we know, the most difficult conditions to forecast. But we are working on separate approaches and models to be working on these conditions. So HAFS, a hurricane analysis and forecast system, is a model dedicated to this type of problem, and we don't expect GAPS to be actually the best under these conditions. And ongoing next steps, we're working on machine learning tools to bias correct first the model, and also to develop these nonlinear multivariate models, statistical models, working in the probabilistic domain. So for the first time, we're developing this in the probabilistic domain, focus on week 2. So here we can see the rock curve after using the machine learning that improves the probability of detection for the 9 meters level. Also the optimization of these hyperparameters of the probabilistic model that are very useful when we move from one location to the other, or variables, or forecast range. So with that, I end my presentation. There are some links here that might be useful, and we're preparing a publication describing the reforecast, and also other publications on the probabilistic model, and also machine learning that I'm very happy to be developing. So yeah, that will be all. Thank you.
Thank you, Ricardo. It was an excellent talk. And so we do have time for questions. So if anybody has questions, you can come off mute and ask them, or put them in the chat. Hendrik, go ahead. Hendrik, if you are talking, you're on mute.
Yeah, I have bad lighting here. You should hear me now?
Can hear you now.
You can hear me now?
Yes.
Okay, cool. So Ricardo, I love your presentation. One of the problems we've had with these kind of works, stuff that you've been doing, is that there is this still more cultural pushback against neural network stuff in general. And I find this really interesting that we are now seeing that the AI and the data-driven models are getting a lot of attention. And I hope that the side effect of that is that the cultural pushback against other AI is going to be less. So I really hope that this is one of the things that we can put into operations pretty soon and can expand to basically all the other components that we have in the coupled environmental system. So very, very happy to see the presentation and very happy to see the potential of the more quote unquote traditional use of AI. Thank you.
Thank you, Hendrik. Yeah, and I welcome everybody to work together. You know that I always like to contribute with everyone, different centers and institutions. So I'm very happy to be further developing this.
Great. Jean?
Hi, Ricardo. Very, very interesting. You know, I'm interested. We'll definitely be in contact at some point, especially when we have our new colleague who will work on AI and wave specifically. So I'm definitely interested to talk. I'm just curious because you presented result for HS because it's all what we always start, but you know, like case of hurricanes, you know, yes, you would know the waves are very dangerous near the hurricane. But what is very dangerous are those long swell that people going to the beach miles away do not pay attention to it. Do you plan to extend this product to other variable like, you know, swell or dangerous swell for coastline application?
Yes. Right now we focus on wind speed and HS because we are in transition to something new, right? We haven't produced this kind of map. But definitely for the Pacific Ocean, I'm concerned about the swell. I showed the bias on the East Coast, so we'll have to be working differently in terms of adapting this methodology to swell because we have multiple swells and then crossing seas. So actually, my honest answer is that I don't know how to calculate probabilities of multiple swells occurring. I mean, I can always select the most energetic swell, but the conditions for mariners at sea is crossing swells. So I'm still searching on how to produce a map that can summarize this information. So yeah, I'm just accepting suggestions. Yeah.
I have one, but it's gonna take a long time to explain. I'll send you something.
Thank you.
Hendrik, is that a new hand?
Yes, that's a new hand, and I still
Okay.
can't see my screen.
1 more minute. All right, go ahead.
Yeah, sure. I think one of the interesting ways to go forward is to link this to some of the work that Andre did with separating out the wave fields in space and time. And I think it would be fantastically interesting to do this on a wave field by wave field basis rather than by the overall wave height. And I know there are people like the folks of SOFAR and a few others are very much interested in that kind of work. But we all know that Jean will have unlimited time to do AI soon, right, Jean?
Sort of, yes.
But yeah, I think seeing how you can well by itself AI is kind of interesting to do the wave field separation and the spatial correlation of that too, and so to expand that to looking at whether or not you have the wave fields and whether you now have these wave fields all the time or not. There's all kinds of other interesting information in there, and we were just actually talking about that in the weather service. What Jan was talking about in terms of the waves far away from a hurricane. The realization on the east coast of the U.S. and in the northern Caribbean is that a lot of the quote-unquote storm surges and inundations are actually wave-driven. And at the weather service, we're actually kind of looking. The U.S. weather service, we're kind of looking at seeing how we can better deal with watches and warnings for these kind of things. So it is very much of an interest of the broader quote-unquote safety of life and property type of work we're doing. So you should have a lot of job security there. Thank you.
Thanks, Hendrik. And Ricardo, I apologize. We are out of time for letting you respond, but please feel free if you have more questions for Ricardo to put those in the chat, and we can continue on the discussion there. And for now, we will move on to our second speaker, who is Paula Camus from the Universidad de Cantabria. Hopefully I didn't mispronounce that too terribly. And she will be talking about applications of data science in coastal engineering. And Paula, we can see your slides.
Okay. Can you hear me?
We can hear you. Take it away.
Okay. So first of all, thank you for inviting me to participate in this wide seminar. During my presentation, we are going to see several applications of data science in coastal engineering. Some of these applications has been developed a long time ago. Others are more recent. They are developed by the Geomatic and Ocean Engineering Group. But the basic algorithm are the same. And also some examples are quite simple, because my idea with this presentation is to give an overview of what is the potential of these techniques in coastal engineering. So it's my presentation is a general presentation, not just focus in one study. So, well, I'll try to, I don't know. I cannot, okay, it's.
We see your second slide.
Yeah, it takes some time in order to pass the, well, and also I can, yeah, okay. So the techniques we are going to see, they belong to data science in the sense that they deal with huge amounts of data, extracting the key characteristics, facilitating the analysis, and reducing the complexity. We are going to focus in 3 techniques. 2 of them are clustering and another one is a selection technique. And the applications can be divided in 3 categories: multivariate characterizations, hybrid methodologies or metamodels, and statistical downscaling. Sorry, but it's okay. Before moving on to the examples, we are going to see how these techniques works and what could be the advantages and limitations. The techniques we are going to see are Camus algorithm, self-organizing maps, and maximum dissimilarity algorithm. So starting with the Camus, imagine that we have a bivariate data example and we want to obtain 16 clusters. So the way this algorithm starts, well, sorry, but my presentation has the way I'm showing my presentation does not allow to see the animation of the presentation. Sorry. Can I try another way to see my presentation?
Yes.
Okay, sorry.
No worries.
Can you hear me? Sorry, I have problems.
We hear you now. We did not hear you before just now.
Okay. Well, anyway, if I it's because I cannot. You have to give me permission in order to share my screen.
Oh, I need to do that again. Okay. Just 1 second. Sorry. Working on that. Morteza, you might need to.
You're good, Paula. Just go ahead and share your screen.
Can you see my screen? Because I'll try to share my presentation in another way.
We currently do not see your screen.
No? Okay. So, well, sorry. Well, anyway, I think I'm going to try it again, and you cannot see. You are not going to be able to see everything. Sorry.
It's okay.
Mm.
So we still don't see a screen.
It's taking time. Sorry.
Okay. It's okay. So
Okay.
there you go.
Okay. So, well, I was here just saying what kind of the thing is here. The way I prepared the presentation, you can see that the iteration process and how this technique works, but because it starts with a random initialization of the centroids, and in each iteration, each element identified which is the closest centroid or the most similar, and then the centroid is updated. So, and the process finished with there's no more updates of the centroids. So in the end, what we obtain is the clusters that the distance between the elements and the corresponding centroid at minimum. Then the other technique is the self-organizing map, which is a kind of Cummings, but in this case, the centroids are located in a lattice. So what this implied is that in the iteration process, not only the winner centroid is updated, but also the ones that they are neighbors in the lattice. So in the end, the map that we obtain is like a flexible lattice that adapts to the data. Then we have the maximum dissimilarity algorithm that is a selection. It starts selecting the most dissimilar one and then the second most dissimilar to the one selected and keeps working like this. So, and it stops when we have the element selected that we wanted. So the way these techniques work condition the outputs, the cluster, the centroid that we obtain. In the case of Cummings, these centroids are uniformly distribution. In the case of the sun, the lattice constrained this distribution of the centroids, but preserve the similarity between the clusters and provides a map with an easy visualization of the results. And then we have the maximum dissimilarity algorithm that covers very well the borders and also the strings, which is what very interesting for our applications. So starting with the first application, which is multivariate characterization, where we use Cummings and Son algorithm. The first example we are going to see is a very simple example. Imagine that, well, we have the time series of the significant wave height, mean period, and mean direction in just one location, and we want to characterize the wave climate. So the usual way is to use wave roses or bivariate probability distribution. If we apply this technique, also there's an animation. But with these techniques, in this case, self-organizing map, we can summarize thousands of hourly C states in just a reduced number of C state types. In this case, 23 by 23 C states. Itself represent one C state, and we can see the relation between the three variables that we are using, significant wave height, period, and direction at the same time. And each of these clusters can represent well-developed swells or roughly C states, and we can also calculate the probability of the occurrence of these C state types. And we can do it more complex. For example, we use, instead of the bulk parameters, the C and the different swells component of C states. Another more sophisticated application is a characterization of coastal hazards. Again, it has an animation and we cannot see all the information, but because here the purpose is the coastal flood hazards, we use a total water level as a proxy. We know that this total water level is defined by a mean sea level, astronomical tide, a non-tidal residual or stone surge, and the wave component. So if we have information time series of these parameters, we are able to define this total water level, the time series. And we can analyze the extreme sea levels. For example, applying an extreme value analysis. And this extreme value analysis has 3 parameters: the location, the scale, and the shape parameters that give us information about how these extreme sea levels behave. And if we have time series at many locations, as we can see here at a global scale, we can obtain these 3 parameters in all these locations. And we also, in this study, we calculate also what is the contribution of each component: the wave setup, astronomical tide, and stone surge. So with this information, we can apply a self-organizing maps considering these 6 parameters and see what is the relation between them. In this case, each variable is represented independently, but in order to see what is the relation between these 6 parameters, we have to focus in the same cluster, in the same cells in every map. After that, we can summarize these clusters in lower number of groups by using Camus algorithm. In this case, in 16 types of coastal flood hazard that give us information about if the streams are bounded or not, or what are the driver dominant. And we can see what is the spatial distribution of these clusters. And in this case, we observe that there are certain patterns of coastal flood hazards at a global scale. The second application of these techniques is to develop hybrid methodologies or meta models. And in this case, we only use the maximum dissimilarity algorithm due to the good characteristics to explore the extreme events. And again, we start with a very easy example. In this case, we have information of the wave condition at deep water, and we want to propagate this information to near the coast in order, for example, to have time series of the wave conditions to design, for example, a breakwater. So we need to propagate every hourly sea state. So instead of doing that, we propose to develop a hybrid methodology that consists in several steps. The first one is to parameterize the problem, because here we are just in a very easy example. We are considering that in the computational grid, we have uniform wave condition as a boundary, and also we have a constant wind. So we can characterize each propagation by only 5 parameters, these 5 parameters. And then what we do is to apply the maximum dissimilarity algorithm in order to select representative cases. Here we can see the combination of the 5 parameters, in gray the historical events, and then in colors the different number of selected cases. With these cases, we run a library of cases, in this case using Swan model, so we have the wave conditions propagated. And for example, in one location near the coast, we can extract for every simulation the result of the significant wave height. And with the result from this simulation of the significant wave height, we can use a radial Bayesian function in order to obtain a multilinear interpolation function that allow us to obtain or estimate what is the significant wave height propagated in just that location near the coast for a combination of the 5 parameters that we haven't simulated numerically. This is just a comparison of how this technique works, comparison of in terms of a scatter plot and time series of a significant wave height, mean period, and mean direction. A comparison between propagate it hourly state dynamically or using this hybrid method. We can do this more complex. Here is what we did for developing DOE database. So in this case, we consider that the wave condition along the boundaries of the computational grids are has a certain spatial variability, and also we consider wind fields. So in this case, we are talking that the parametrization of this problem implies a lot of wave condition and wind conditions and many grid points. So in the process of developing an hybrid methodology, we introduce the principal component analysis in order to reduce the dimensionality of the problem and do the selection and the reconstruction in this reduced space. And here we can see the validation of the significant wave height period and direction in one location where we had records from a buoy. But we can also develop meta models that not only consider parameters that represent the climate forcing, and this is an example of a meta model that it's called HiCrew, and it was developed for reconstructing the run-up in a beach that is protected by a coral reef. So in this case, several configurations of these coral reefs were simulated. So we introduced these parameters, geometric parameters that define the slope, the width of the reef flat, the friction coefficient, and also the slope of the beach in order to define, in this case, these multilinear interpolation techniques that allow us to reconstruct the run-up for other configuration based on these 7 parameters. Just to mention that the last development that we have done within GeoOcean group are high beat and high float. They are developed within a tropical cyclone inundation system. In these cases, high beat was developed to obtain the wave setup and infragravity wave, and in this case using X-beach model, and high flow was developed for obtaining the flooding depth using in this meta model the least flat model. And then the final application is a statistical downscaling, and in this case we use Cummins algorithm. And the statistical downscaling has 2 also application to obtain wave climate projection and to develop climate emulators. The basic idea behind this statistical downscaling is that we establish a relation between a larger scale mid-ocean predictor and a local dynamics. In terms of a larger scale predictor, we can use sea level pressure fields or winds or even surface temperature. And regarding local dynamics, we can be interested in waves, western surges, or total water levels. And we establish this statistical relation. And how we do that? We consider that all the daily atmospheric conditions defined by this large scale predictor can be clusterized in a certain number of weather types or weather patterns. imagine that in the our study domain, we can summarize these daily conditions in just only 4 weather patterns. So what we do after that is for a certain point, see what are the ways that has happened during all these daily conditions that were represented by these 4 patterns. So for each weather type, we can have, or we can define what is the distribution of the significant wave height, for example. So once we have established this relationship, we can calculate the probability of each weather type, and multiplying the probability of the distribution of the significant wave height within each weather pattern, we can infer the total distribution of the significant wave height for that specific location. So the main application of this is to obtain wave climate projection. So we go to a time horizon, a time slice, we can calculate which is the new probability of this weather type, and preserving this statistical relationship, we can infer what could be the new distribution of the significant wave height and compare with the one that is for the current climate, and see what could be the changes. For example, this has been applied to obtain the wave climate projection in Europe. So the first step is to define what are the could be the weather types in this case, in the North Atlantic over North Atlantic Ocean. Then we can calculate what is the changes of the weather types for different climate change scenarios and time slice. And then we can see what are the changes in the significant wave height. This is an advantage in the process of calculating the wave climate projection, because there is a cascade of uncertainty in the process, because we have to consider different climate change scenarios and also an ensemble of global circulation models. And because they have these statistical techniques has a very low computational effort, we can download many global circulation models. This is what we do when we obtain global wave climate projection. And here we can see the result just for the west coast of the South America. That one of these advantages is that we can quantify which is the uncertainty, just not only so what is the mean changes, but what could be the uncertainty in the different parameters of the sea states. And the final application is to develop climate emulators. And here is an example just applied also in coastal flooding risks. So again, we use this proxy of total water level, which is composed by the wave component and the storm surge. So we have the parameters that define these components of the total water level. But usually we only have historical data, and the extreme sea levels are usually a reduced sample. So with this climate emulator, we can simulate synthetic events. And we use this statistical relationship. So imagine that in the area we are wanted to develop the climate emulator, we have characterize our weather situation, atmospheric situation, by, in this case, 36 weather types. So we know that for each day, we have a daily weather time assigned. And in this daily weather type, we know what are the distribution of the waves and, for example, storm surge. In this case, instead of using bulk parameters, we consider 1C and 2 swells. So we have a multivariate local dynamics. No? So with this climate, once we have this established this statistical relation, we are able to simulate daily weather types, and then within each daily weather type, what could be the waves and the storm surge that could happen for that weather type. And we can do it in a even more complex way. And this is what Tesla emulator do. That we here the interannual intraseasonal variability is introduced by much larger predictors. So in this case, we are able first to simulate this interannual variability, then intra-seasonal variability, and then again the daily and the subdaily conditions. So in the end, we are able to generate synthetic events that they are dependent. These local dynamics are dependent between them, and also dependent on the climate, and on the climate in a different scale of time and space. And just only for finishing, I would like to mention the Blue Math, which is a open source tool code in Python, where you can find these different techniques or different pieces that allow to define hybrid downscaling or statistical downscaling techniques for the different coastal engineering projects that you want to solve. And this is just my presentation. Thank you very much.
Thank you. That was a great presentation. So we can open it up to questions now. So you can raise your hand and come ask your questions out loud, or if you're having audio issues or would just prefer, we can also use the chat. All right, we have a question in the chat. So KMA needs initialized with initial K, which means we a priori know none of the clusters beforehand. Can this limitation be removed or circumvented?
Well, if I understood correctly, the question is that you need to establish what number of clusters you wanted to obtain since the beginning. Yes, it's true. But the way to it could be a limitation, but in order to overcome this limitation is to perform a sensitivity analysis and consider different numbers of clusters in the beginning. Yeah, but it's a limitation. But yeah.
Thank you. All right, we've got time for a few more questions if anybody has additional questions. So I'll ask one. So these are a great tool set that you showed and a lot of great work. So what is your next step that you are excited about tackling?
Well, at this moment, we are also working in developing meta models in order to simulate flooding, but in compound flooding. So, and now in our group, we are working in simulating the compound flooding in estuaries. So we are introducing not only the coastal or the oceanographic drivers, but also the ones that came from the inland, like river discharge or precipitation. So we are increasing our field of applications. Yeah.
Awesome. All right, Yaren, and then we've got 2 questions in the chat, and that'll probably be all the time we have. Go ahead.
Thank you, Paula, for a very interesting talk. When I see the SOM analysis, then it reminds me of a type of classifications that's called synoptic classification. And the synoptic classification is related to a classification of synoptic systems that let's say the forecasters are used to and know that they exist. And then it connects somehow to the physics, yeah, in a way. And when you, I guess it connects to the first question or not, how can you connect what you get from the machine learning type, like the sum, to a real physical situation? If you choose 20, it will give you 20. If you choose 10, it will give you 10 clusters. So did you see a good correlation between the synoptic classifications and the choices of some, or it's just patterns that the computer kind of extract and fits, and it's reasonable to use them?
Well, also the problem is how many, no? How many patterns we are necessary. Of course, it depends on the problem you want to analyze. So maybe the better is you want that patterns for usually to reproduce or to relate it to certain local dynamics. So one way could be introduce this dynamic also in the classification. For example, this is something that we do and we call semi-guide regression classification, where you can first you have to do a linear regression between the local variables and the synoptic, no, or the atmospheric, in terms of regression, and then you can introduce that information in the classification. So the classification has information of the local variables, but in a way that you also eliminate maybe a very information that is can contaminate in some way. But the one way could be introducing local dynamics or the predictant in the classification, and before introducing these local dynamics, perform a multilinear regression in order to eliminate maybe information from the local variable that is that has like too much detail. But at least this is something that we did, just to focus very much on the problem. But of course, you have still the problem of how many patterns.
Yeah. So
then in the end, you have to make a sensitivity analysis on the response that you want to obtain using that statistical relation between the predictor and the prediction.
If there are, like in the physics, we see, I don't know, in the East Mediterranean, I think the number was 19 or 17 synoptic classification. Do you think if you choose 17, you will get the same more or less patterns, or the computer will divert from when there are ones that are very not repeating so often or something like that?
No, the thing is, the more patterns you have, the more details you are going to obtain, but the main features are going to be there. Maybe you are going to obtain is like splitting some patterns into, for example, giving with differences in some details, but I think all the physics are going to be contained.
Okay.
All right.
Thanks.
Thank you so much, and thank you for all of the questions. Unfortunately, we are out of time. We've got 2 more questions in the chat. Paula, if you don't mind taking those, or reach out via email. And I want to say thank you to both Paula and Ricardo one more time. And also, we look forward to seeing you all in about 3 weeks for our next WISE Zoominar. And thank you again for everybody dialing in today. All right. Bye, everybody.
Thank you.